Hello everyone. Now the next important question is rules of inference. So what are these rules? Totally there are 6 rules. Let us study one by one. The first one is rule of conjunctive simplification. Okay. So according to this rule, consider any two propositions P and Q. Okay. If P and Q is true, then P is true. This is the thing you need to remember. If P and Q is true, then P is true. That means, how to write this? If P and Q is true, it implies that P is true. Okay. So this is the rule of conjunctive simplification. Next, rule of disjunctive amplification. Here, for any two propositions P and Q, if P is true, then P or Q is true. That means if P is Q, that implies P or Q is true. Okay. So now the third rule is rule of syllogism. So here for any three propositions P, Q, R, if P conditional Q is true and Q conditional R is true, then it is P conditional R. So what is that? See here, if P conditional Q is true and Q conditional R is true, then that implies that P conditional R is true. Okay, so that is P conditional R. So this is the rule of syllogism. Next, fourth one, modus pons. It is also called as the rule of detachment. Here, if P is true and P conditional Q is true, then Q is true. So how to write this? If P is true and P conditional Q is true, then Q is true. So this is the rule of detachment. Next, modus tollens. If P conditional Q is true and Q is false, then P is false. How to write this? See, if P conditional Q is true and Q is false. False means I should take negation here. Q is false, then P is false means negation of P. Okay. Last one. Rule of disjunctive syllogism. If P or Q is true and P is false, then Q is true. That means P or Q is true and P is false means negation of P, then Q is true. Q. So these are the 6 rules of inference. Now the next important question is mathematical induction. Okay. See, the given question is 1 square, 3 plus 3 square plus 5 square and so on up to plus 2n minus 1 whole square is equal to 1 by 3 n into 2n minus 1 into 2n plus 1. So we have to prove this by mathematical induction. See, as we know, there are 2 steps in solving this by mathematical induction. So the first step is basic step. So whereas in case of basic step, we are putting n equal to 1 in LHS and in RHS. So what is LHS? That is 2n minus 1 whole square. Okay. So whenever there is n, put 1. So what it becomes? 2n into 1 minus 1 whole square. That is equal to 2 into 1 is 2 minus 1 whole square. 2 minus 1 is 1. 1 square is 1. Now RHS. So what is there in RHS? 1 by 3 n into 2n minus 1 into 2n plus 1, that is is equal to 1 by 3 into 1, 2 into 1 is 2, 2 into 1 is 2. Now this is 1 by 3 into 2 minus 1 is 1, 2 plus 1 is 3, 3 get cancelled, it is 1. Therefore, the basic step is verified, that is LHS equal to RHS. Now, the next step is induction step. So, what is there in the induction step? First, we have to put n equal to k. So, the equation becomes when we put n equal to k, we get this equation. After this, we have to put k equal to k plus 1 in LHS. Now, what it becomes? See here, 2k minus 1 whole square. Okay. When you put k equal to k plus 1, it becomes 2 into k plus 1 minus 1 whole square. That is equal to 2 into k, 2k plus 2 into 1, 2 minus 1 whole square. That is equal to 2k plus 1 whole square. Now, you need to add this on both the sides. So, adding 2k plus 1 whole square on both sides. Okay. Now, what it becomes here? Add this on both the sides here. So, the equation will be plus 2k minus 1 whole square plus 2k plus 1 whole square, and that is equal to, see the RHS, 1 by 3 k into 2k minus 1 into 2k plus 1 plus 2k plus 1 whole square. Now, see here, let me take the LCM. So, what it will be? 3. 3 is the LCM. Now, here, k into 2k minus 1 into 2k plus 1, and here 1 3s are. So, this becomes 3 into 2k plus 1 whole square. Now, here I will take this 3 outside. Now, what is common in these two? This and this. 2k plus 1 is common. So, here 2k plus 1. Now, what is left here? K into 2k minus 1 plus 3 into 2k plus 1, because it is whole square. Okay. So, now 2k plus 1 divided by 3, and here we have, let us cross multiply, k into 2k, 2k square minus k into 1, k plus 3 into 2, 6k plus 3 into 1, 3. Now, see here, 2k square, 6k minus k means 5k plus 3. Now, you have to simplify this equation. If you multiply, you should get 6. If you add, you should get 5. Which are those numbers? 3 and 2. Okay. So, now, here we have 2k square plus 2k plus 3k plus 3. 5k is written as 2k plus 3k, and the remaining as it is. Now, 2k plus 1 divided by 3, and here in these two we have to take common. So, here the common is 2k, k plus 1 plus, here common is 3, k plus 1. Now, 2k plus 1 divided by 3, and here we have 2k plus 3 and k plus 1. Now, I will write this as, see here, k plus 1 divided by 3, okay. Next, 2k plus 1. Next 2k plus 3. Once again, I will write this as k plus 1 into 2 into k minus 1, k plus 1 minus 1, okay, and 2 into k plus 1 whole divided by 3. So I have written this as this. See, if you compare this, what I have written here, 2k plus 2 into 1, 2 minus 1, that is nothing but 2k plus 1. 2k plus 1. Okay. Next, see this one, 2 into k, 2k plus 2 into 1, 2 plus 2, 1. So this becomes 2k plus 3. That is here. Now, compare this with your proof. So, 1 by 3, yes, 1 by 3, n is nothing but k plus 1. Next, 2n minus 1. So, 2n minus 1. 2 into n minus 1. Next, 2n plus 1. That is 2 into n plus 1. 2 into n plus 1. So, this is the proof of mathematical induction. So, here there are few questions. Explain the different logical connectives along with their truth tables. So, what are the logical connectives? As we studied, negation, okay, conjunction, okay, disjunction, exclusive disjunction, conditional, biconditional. So, all these come under logical connectives, okay, which is already been covered. Okay, next, list the different laws of logic and draw the truth table. Laws of logic are nothing but idempotent law, okay, commutative law, associative, distributive, all these come under here, and explain any two laws. But if you know the laws of logic, you will be able to explain all those. Next, so this is already been covered. Next, explain different types of functions with arrow diagrams. Functions nothing but constant function, onto function, one-to-one correspondence. Okay, so arrow diagrams are nothing but like this. Function. So these are nothing but the arrow diagrams. Okay, so all these three questions have been already covered. Now consider this question. Consider the following argument. Okay, what is the argument here? I will get grade A in this course, or I will not graduate. I will get grade A in this course, or I will not graduate. Next, if I do not graduate, I will join the army. If I don't get graduation, then I will join army. Now, I got grade A. Therefore, I will not join army. So, this is the argument being given. Now, we have to write it in the form of propositions. Now, first one is, I will get grade A. Let it be P. So, what is P? The proposition P is, I will get grade A. Okay, next, I will not graduate. Let Q be, I will not graduate. Okay, next, if I do not graduate, I will join the army. I will join army, let it be R. I will join army. Now, see here, we have to write this in the form of propositions. First, I will get grade A means proposition P in this course, or I will not graduate. I will not graduate. P, Q. P or Q means what? P, I will get grade A, or I will not graduate. This is completed. Next, if I do not graduate, see, if word is used here, that means it is conditional. If I do not graduate, means Q, then I will join the army, that is R. If I I do not get graduate, then I will join army. Next, I got grade A. I got grade A means P. I got grade A. Then, therefore, I will not join army. I will not join army means negation of R. So, this is what the given argument is. Now, we have to verify whether it is valid or not. See here, P or Q can be written as Q or P using the commutative law. I will write it like this. Okay, see here, P or Q is nothing but Q or P using the commutative property. Okay, and this Q or P is logically equivalent to negation of P conditional, negation of Q it is, okay, negation of Q conditional P. So, P or Q is written as Q or P using the commutative property, and Q or P is logically equivalent to negation of P conditional P. This you can verify using the truth table also. Okay. So, this we can write it as negation of Q conditional P. Now, coming to here, Q conditional R can be written as, means it is logically equivalent to negation of R conditional negation of Q using the contrapositive rule. Contrapositive rule. Okay. See, what is this contrapositive rule? P conditional Q, if we have, that can be written as negation of Q conditional negation of P. This is how it is written. Now, let me write this. P or Q is nothing but this one, and Q conditional Q is nothing but this one. Okay, now let me write this. This is negation of Q conditional P, and this is negation of R conditional negation of Q, and here is we have P, and the answer is negation of R. See, if we consider only this much, okay, so if we consider the rule of inference, okay, so in the rule of inference, one thing we have, if P conditional Q and Q conditional R, then the answer is P conditional R, okay, but here we are getting negation of R. Therefore, no rule of inference is applicable here. Therefore, this is not valid argument. This is not an valid argument. So, this is the answer. Because whenever we write this argument in the form of propositions, we are supposed to get this argument applicable for any of the rule of inference. But here, this is not applicable for any of the rule of inference. Therefore, this argument is not a valid argument.